So we are talking about chemistry and measurements. And what's the big deal here? I thought this was kind of neat. If you just do a little Googling on this, you find out, like in the forensic science lab, 63% of the wrongful convictions are due to screw-ups, right? Or in Saudi Arabia, you know, or I guess they must have bought some of our missiles or something, but they screwed up on the rounding, right? In lab, we did some calculations. How many digits do I report my answer to, right? That's important because not all those digits are valid. They're all not significant. So they screwed up there, and some people ended up dying on it. We'll talk about density. Okay. And another thing we'll talk about is this size. And it's a way to write really tiny and really big numbers. For example, like 10 to the fourth is 10 to the fourth meters is a skyscraper, right? 10 to the negative 4 meters is a little bacterium, okay? So negative exponents we're going to get into are really, really tiny, small numbers. Matter. Did that list make it around all the way yet? That's going around? Okay, it's still coming around. So poor Bowdy and me are the only ones that can ask questions. So, well, let's not ask a question yet. All matter, all stuff, whether it's solid, liquid, gas, doesn't matter, we call it matter, right? So all matter can be divvied up into either a substance, I like to call it, I don't know why they don't write the word pure, sounds better, all right, a pure substance, or it's going to be a mixture. And a mixture, just take a bunch of pure substances and mix them together, then you'd have a mixture. So how do you go back and forth between these pure things and their mixtures? They just call them physical processes. Because you're not really changing anything, right? You're just making it pure or impure, really. So they call that physical properties. Now, if you are a pure substance, okay, and then you're divvied up into either elements or compounds. So now let's pick on Bowdy. Hopefully I get that list up here quick, Bowdy. What's the difference between an element and a compound? Ooh, really good. Did you hear what she said? An element has just one, and a compound has multiple elements. What does she mean? First, where are all the elements? They're all on the what table? Periodic table. All the elements, right? So here's a molecule. Go by what Bowdy said. If you're a different color, so these are bonds, right? If you're a different colored hunk of plastic, you're a different atom. You're a different element. So would this be considered an element or a compound? Mia. Mia, would this be an element or a compound? All right? Compound, because there's different colors in there, right? I got to remember Paul. I remember Paul. There's a Paul in here. Paul. Element or a compound? You have this whole bunch of these flying around. It'd be an element. I think there's a Dylan in here. I remember a Dylan, right? Dylan? Element or a compound? Element. It's confusing, right? Because there's more than one. But it's the same thing. So it's an element, right? And a lot of elements exist like this in nature. For example, I should be writing on here in case anyone's listening. Hydrogen doesn't exist in nature as bare hydrogen atoms flying around. Nope. It exists like this. Right? It's still an element. Nitrogen exists in nature like that. Oxygen. So many gases exist like that. But they're still elements. Okay. So to go between elements and compounds, right, there's your chemical reaction. We're actually changing what's at the molecular level. So these guys react, boom, and then we get our molecule back somehow, right? And we'll talk about reactions and activation energies and all that kind of stuff later. Okay? So that would be an example of a chemical reaction. Now, if it's a mixture, take a bunch of these molecules, take a bunch of these molecules. Now you got a bunch of them. Now you'd have a mixture. Okay. So the mixtures, there's only two types, homogeneous and heterogeneous. Is my sheet made it around yet? Dylan, oh, let's pick on Tanya. Tanya, how can you tell the difference whether this mixture of these guys is going to be homogeneous or heterogeneous?
Because on homogeneous, they're all compound of the same and they look equivalent throughout the whole substance. But heterogeneous is you can see the difference.
There's the key, what Tanya said at the end. Do you hear it? If you can see the difference, then it's a heterogeneous mixture. If you can't see the difference, it's a homogeneous mixture. So let's take a look at a couple of these. We've got water. Here's a bunch of water. Where would you put this on the chart? Megan, right? Megan, where would you put this on the chart? Water. Homogeneous mixture. Because it looks the same throughout. And she caught it, right? I was hoping that she would say, what? Compound. But she knows that I'm not, you know how expensive it would be to get ultra pure water, right? Just H2O molecules, that's it. No dissolved gases, no nothing. That's extremely expensive. So water is almost always a homogeneous mixture. There's a lot of stuff in there, right? Oh, now I can pick on some people. Emily, how about salt and water? How about just salt first? Where's Emily? You gotta look at this way. Emily. Just salt. Hopefully you don't eat too much of this stuff. Compound. Good, because salt is actually, table salt is actually NaCl. So good guess. That's definitely a compound. Okay. So I take the two. Let's pick on Lorena. Now, how would you describe this? Heterogeneous mixture. Because you can see the difference, right? You get all this stuff to dissolve nice. Then it would be anybody? What type mixture? Homogeneous mixture, right? You can get it all to dissolve somehow. Right? Water and dye. Okay. Guess I'll just have to use this one. Here's my water. Rebecca. Here's my water. Here's my dye. How would you describe this on this chart? Where would it fall? Yes. Heterogeneous mixture, right? Heterogeneous mixture. Good. Okay. And you get the whole thing to dissolve and get it all right. You'll turn it into a homogeneous mixture if you wait long enough. Okay. Chemical or physical process? Kenneth. This is probably the most boring demonstration I can get you. Ice melting. Yeah, there's heat from the room that's being absorbed. Chemical or physical process? Physical, right? Because nothing's changing. It's H2O solid going to H2O liquid. Nothing's changing. So that's definitely a physical process. It's still this, H2O. But, you know, it's just changing state, going from solid to liquid. Definitely a physical process. Steel wool and fire. All right, Sydney. Steel wool, so shredded steel, fire. Where's Sydney? Sydney. Steel wool and fire. Definitely chemical, right? It's burning. Isn't that strange? Iron will burn if you get it in the right form. It's actually, you're forming iron oxide. It's oxidizing. Distillation. Okay, before I ask you, here's a distillation apparatus, and they have a little movie of it. Okay, so you have this container, and it has two different compounds in it, or two different elements. You just know that they're two different at the molecular level. Two things. So it's a mixture. So what they're going to try to do is use distillation to separate it out into its pure components. So what they're doing is, what's missing is that big vials down here. And notice all the blue atoms are coming out first. So they're just heating it up. So now once all the blue molecules are gone, then the boiling point just shot up to the next one. So what's really happening here is this. Big money. Why? You get that black gold in the bottom of the desert, right? Oil. And then you distill it. What are you doing? Well, you just take this black mixture, right? You put it in some big vat, and then you're just going to slowly heat it. And what's going to boil off first is the stuff with the lowest boiling point, the stuff that boils the easiest, the stuff that really, really smells, the stuff that's probably the most expensive, jet fuels. They're the most volatile. They're the most explosive. They're going to boil off first. So look at all these tubes. It reaches that, one of these tubes is for that jet fuel. It's going to go to some big container for jet fuel. Really expensive, make a lot of money. So all the jet fuel boils off. All right, and yet there's computers and sensors in here. It knows that all the jet fuel's boiled off. Now it's coming off next. Gasoline that you put in your automobile. It's the next volatile thing. So the boiling point goes up a little bit, and that's how it knows to switch the valve. So it switches the valve, now you have the gasoline coming off. And it goes into another big reservoir, right? They use every part of that oil and make a lot of money. So that's what's going on with a refinery. Okay. Oh, we didn't answer the question. Let's see if, I haven't picked on Stephen? Stephen. Distillation. Physical or chemical process? Now this, I wish they would have the word process down here, because that's really what we're supposed to be talking about. But distillation is it changing chemicals, though? Ask your question this, right? Because you had the jet fuel, you had the gasoline, you had all those other compounds in the oil. Distillation is just separating them out. So it's not changing the compounds, it's just separating them out. So it must be a physical process. This distillation is a physical process. Significant figures. Okay, I need some help for this one. If I can get, how about, let's pick on, who haven't I picked on yet? Giselle and Manuel. I need your help, Giselle and Manuel. Okay. Manuel, here's his ruler. Giselle, here's her ruler. So we've got a ruler with lines, and we've got a ruler without lines. So usually when you're reading a book or you're working wherever your field is, engineering, whatever you end up, all you see are the numbers. You don't see the tool, right? Now we can tell one tool really sucks. The other tool is a lot better, right? But how is that information relayed? It's relayed through significant figures. So what I want, let's see, let's have the ruler without lines first. Just measure this tabletop next to Connor. Just do your best, right? And it's in centimeters. And just tell me what you, make your best guess there. 40.6? Oh, you're talking about, so there'd be 46, right? Because that's 50. So 46. Okay. Thank you, Giselle. Let's say 46 centimeters. Okay. And Manuel, same thing. Well, let me grab that for you. Thanks, Giselle. $45.5. Okay. So first, if you could see the tool, but you never get to see the tools, one is much more believable than the other one, but you never get to see it. Instead, you just see the measurements. And you look at the measurements, one is much more believable than the other one. Right? This one is. Right? It's just got more digits. And they call those significant figures. So there would be how many significant figures here? 3. And there's how many here? 2. Okay, so this is a better tool. Or they were more careful, or you don't know what. But it's a better measurement. Okay. Now, Giselle could have kept going here, 46.69283, but you know she's just lying, right? But if you just look at the number, you couldn't tell. So that's why you kind of got to be careful. Determine the number of sig figs in each measurement. So we'll just, I don't know, let's just start with, who's after Giselle? I'll get these names now. Sydney. How many sig figs? She's counting 1, 2. But what if Manuel would have said 45.50? Right? There would have been another sig fig. So likewise here, someone read it to the hundredths place. It's not a 1, a 2, it's a 0. So there's not 2 sig figs, everybody, there's 3. How about B, Emily? 4. 1, 2, 3, 4. Exactly. How about C, Dylan? Oh, it's a trick question. There's only one. Huh? There's only one. There's only one sig fig there. There's a much easier way to do this than just guessing and looking at it, and we'll get to it. But I want to get you through this first. How about D? Stephanie. Ooh, good guess. There's only 2. How about E? Kendall. 1, 2, 3, 4, 5. Yeah, all of them. 6. Okay, now there's got to be a lot easier way to do this. And there is scientific notation. Then there's no guessing at all. We write the number in scientific notation, and that's some number A, which is a number between 1 and 10, and n is the number of times we have to move the decimal place to get that number A between 1 and 10 in our measurement. And then all we do is just count the number of digits that exist in A, and we're done. That's our sig figs. So much easier. So let's do this column first. Here's our measurement. I'll show you how to do this first one. Here's my decimal place. I need to move it either right or left and get it so that it's a number between 1 and 10. Well, my number would be 8.5, right? So I gotta move it that way. I'm gonna move it 1, 2, 3 places. So my number that I'm left over, you write everything that's left. 8.501. You write everything. Those zeros disappeared, so we don't worry about them. Right? I got a number between 1 and 10. 8.501. Now I moved it 3 times. Times 10 to the third. Now that 3 either has to be a positive 3 or a negative 3. Me, I hate memorizing stuff. I much prefer, what is it doing? I much prefer this. Really small stuff, negative exponents. Really big stuff like skyscrapers, positive exponents. So it wouldn't be a positive 3 because it was, what, 0.008. It's a dinky number. It has to be a negative 3. Okay. And then how many sig figs would I have? 4. You just count them. 1, 2, 3, 4. Count everything. So it's so much easier than just guessing. Okay. So, well, let's just ask somebody here. All right. Where did I leave off? I don't know. Maybe I left off at Alyssa. How would you write this number in scientific notation? 3.65 times 10 to the 6. Good, I agree. And then how many sig figs would you have, Sarah? 7. Exactly. Oh, how about Paul? How would you write this one in scientific notation? Perfect. Perfect. How about the number of sig figs, Bowdy? 5. So you getting the hang of this? Megan. 3.825 Yeah. Everybody agree? How many sig figs do you count in there? Let's just make it more random here. Kendall? How many sig figs do you count in that mess?
7.
Oh, I think it's there. I count 10 too, right? 10? Everybody agree? Okay, so that's the idea. I think you got the idea on this, right? So just stop me and ask anywhere along here. This is where I think things can get a little more confusing. Because what we have to do is we have to add, subtract, multiply, divide. This is where those guys in Saudi Arabia really screwed up, was in their mathematical calculations. So for example, if we take these two guys' measurements, whoop, all right, maybe they're making something simple. They're making tables, right? Some really rich dude wants a table, but we're using the same parts, right? This guy's making parts. This guy's making parts. We got to put them all together. Well, we can't. You see the problem here? How are we going to make sure we agree that all these parts are going to fit? Because we have different sig figs here. So we just have to keep track of them. How do you keep track of them? So then in the end result, these parts are going to communicate. They're going to work. Everything's going to be hunky-dory. Here's the rules. When we're doing adding or subtracting, you always report your answer to the smallest resolution. Okay? So resolution is that decimal place. All right? It doesn't matter what the number is. It could be right? It just depends on where it's at. For example, resolution here is tenths, hundredths, thousandths place. tenths, hundredths place. And you can put a number in front. Doesn't matter. The resolution is to the tenths place. 762. Well, the resolution is to the ones place. So it's just the smallest digit that's in that reading. Make sense? That's what the resolution is. Let's go to the furthest to the, what is that, right? And you're good. Okay? When you're doing multiplying and dividing, report your answer to the smallest number of sig figs. Okay? So I think it makes the most sense if we just do some. Okay. Now what helps me though is I like to I know I'm just doing adding and subtracting here, but regardless what I'm doing, I like to underline because then it's just easier for me. And then I can see that, underline that last digit. So I can see, first it tells me where the resolution is. The resolution is only to the tenths place. Okay? So I have to report my answer to the tenths place. For me, doing all these problems, I always just do everything on the calculator, and then I round to the tenths place. So you do everything on the calculator, you end up with 3.53. Right? Sometimes this is good enough because that's convention. People like to underline that last significant figure. This 3 is garbage, but it's not good because what if people aren't used to that convention? So just write 3.5. Okay? So try this one. Try B. Underline that last digit so you can easily identify the smallest resolution. Do it all in your calculator, and then report your answer to the correct number of sig figs. Lauren, did you bring your calculator? Where's Lauren? Lauren, did you bring your calculator? Okay, so did you get not your final answer, but when you did all the math, what did you end up with? 1.7109? All right. That's what I got. Did you get that, you said? Okay, 1.7109. Okay, but that's too many digits. Which number should I be underlining in that numerical answer, Emily? Which number should I be underlining in this 1.7109? 7. Right? Because it's the worst measurement. This dude only did it to the tenths place. Worst measurement. So you got to report your answer to the worst measurement. So 1.7. It would have been 1.8. Giselle, if what? This answer would have been 1.8 if what? Yeah, if the number next to it was greater than 5. And then that would have been 1.8. Okay. We're doing B now. Now we're just doing multiplying and dividing. So you have to do everything on the calculator. We're doing this one now. You have to do everything on the calculator, report your answer to the measurement with the fewest sig figs. So you can do the underlining thing, but it really doesn't help much. But maybe it does. Maybe it helps you. But do everything on your calculator. and report your answer to the smallest number of sig figs. Rebecca, did you bring your calculator? Okay, great. What did you get as a complete answer here? No rounding at all. What did you get? 1026. Okay. Too many digits? Maybe not. You can only report your answer to how many sig figs? Oh, Audrey? How many? Well, this one has how many? He actually has 3. If you're going to write this one in scientific notation, well, what I want to do is figure out how many sig figs are in each one of these. Then I got to report my answer to the one with the smallest number of sig figs. So the trick really is writing these in scientific notation, and then you tell it by the A number. How would you write 3.80 in scientific notation? Once you see this once, it won't be so bad. It's already between 1 and 10, right? So you'd have to write 3.80 times 10 to what power? We didn't move the decimal place at all, so it has to be 10 to the 0. Anything to the 0 power is just 1. I don't know if this helps you, but that means there's just how many sig figs? There's 3. So there's 3 here. Everybody there's 2, and everybody there's 2. So report your answer to 2 sig figs. The answer would be 10. Problem with 10 is newspapers. It's 10 miles down the road. Well, you and I know that could be 11, could be 9, but it's somewhere around 10. So numbers like this, 10, 100, 1,000, 200, 300, they want more information. Either you have to write, I'll just write in scientific notation. It would be what in scientific notation? 1.0 times 10 to the first. That's the best way to write your answer. Because you'll get points docked for that guy. It's not clear how many sig figs there are. All right, try C. Try C. I would figure out the part in the parentheses first. And you don't do any rounding until the very end. Don't do any rounding at all until the very, very end. Okay? Figure out the part in parentheses first. And then do the rest. And don't do any rounding till it's all over. All said and done. Let's see if anyone wants to make a guess here. As a final answer, let's pick on, who have I picked on? I think I got everybody, have I? Emily, have I picked on you? Let's pick on you anyway. Emily. Where's Emily? Emily, final answer. What's your guess? Final answer. She says 11. Does everybody agree? Now, one thing that I like about Emily's answer, 11, is that there are how many sig figs in her answer? 2. So I said do the part in parentheses first. So if you do the part in parentheses first, you add these two numbers up, 3.8 and 2.72, you get 6.52. And I'm underlining that 5 because, right, it has to go to the tens place. And I didn't erase that 2 because you don't do any rounding to the very end. So my final answer is going to be 7.42 times 6.52 divided by 4.085. And the answer in all its glory is 11.84293758. Okay. However, what number should I be underlining in this big mess? What number should I be underlining? The 8? How many sig figs should be in this final answer? There should be 2. Because I've got 3 and 7.42. I've got 1, 2, 3, 4 and 4.085. But I only have 2 up here with the 6.52. So I better report my answer to 2 sig figs. So she was really close. It's just not 11, it's 12. It's 12. Okay. So we'll come back and do some more of these. Let's just talk about this stuff. Base units, you just have to know it. For length, they like the meter. This is the metric system. And you got to know the symbols, little m. Mass, kilogram. kg. They're already getting into prefixes there. Time, it's the second. Temperature, Kelvin. Amount of substance, mole. Okay. For our British system, what's our unit for mass? Man, if you know this, you're doing really good. It starts with an S. Isn't that weird? Slug. Did you ever hear that? Oh. And you never will, I don't think. Okay. Derived units. So all that is just taking the base units and putting them together. Length squared, well, you get meter squared, right? And that's area. Volume, length times width times height. Well, 3 lengths multiplied together, you get meters cubed. Density, mass divided by volume, so kilograms over cubic meters. There's another unit for volume. Besides cubic meters, there's cubic decimeters, which is 1 big L, where big L represents liter. Some people spell it L-I-T-R-E. I think that might be the British way. A cubic centimeter is 1 ml. What's an ml? Milliliter. Yeah. Okay. So let's see if we can read these. Mia, how would you read DG? We haven't really talked about these prefixes, but maybe you know them. DG. You got a prefix and then a unit. Little d. This was probably years ago. Now the G part's definitely grams. But what is the D? Anybody know? Deci. cm. Anybody? Centimeter. So you've got the meter part from the M. The C is the centi. MS. How about MS, Sarah? Now the S part would be second. Would be milli. So the whole thing millisecond. KL. Kilo liter. All right. Okay. So not only do we have to know, how to read this stuff, but we have to know where to put the numbers. So if you have deci, centi, milli, kilo, and then you have the unit on its own on the other side, how many? Right? Is it 10? Is it 100? What? Now, for me, it gets confusing. So what I remember is when I put a number in here, it always, always, always goes with the prefix, except for kilo. That really helps me. So that means I'm going to have a number in front of the deci, I'm going to have a number in front of the centi, a number in front of the milli. These guys are just going to be ones. So the number always goes in front of the prefix except for kilo. So I'm going to have a 1 over here. Now I just got to know what those numbers are. How many decis make a whole? 10. How many centis make a whole? 100. That's the only one that's easy, right? Because 100 cents in a dollar. How many millis make a whole? 1,000. See, so it's just factors of 10. That's the nice thing about the metric system, right? All right. If you have 1 kilo of something, that means you actually have how many of them? Not 10, not 100, but 1,000. Okay. So know this. Definitely know this. In other words, you've got, fill it in down here to make sure you're following here. Fill in the numbers. You've got deci, centi, milli, kilo, and then whatever the units are. All right. So it's pretty much the same thing, right? 10 decis, 100 centis, 1,000 millis, 1 kilo. All right, pretty much the same thing. Okay. Density. Okay. You might have seen this before already. Drop these in water, what's going to happen? What's that?
One of them is going to float.
One floats, one sinks. Which one floats? Diet Coke. Why? It's less dense. There's less mass for the same volume. Because they definitely have the same volume, same can, but much less mass. Why is there less mass? What's the difference? I massed it out. This is how much sugar you're consuming in 1 can of Coke. Have 1 can of Diet Coke, this is what you're consuming for the sweetener. What is that? NutraSweet? They call it aspartame, right? It's 1,000 times sweeter than sugar. Okay. So Coca-Cola should sink. All right. And the other guy floats. Right? Less dense. Okay. We've got about 5 minutes left. So this is really no big deal. Let's see if we can finish up these. So work on, work with the folks around you and see if we can get answers for these. Okay. And I'll write the final answer down there and make sure that you can get it. Yep.
So does the 0.3 and 0.5 not count this? It's just
So yeah, so if you're not sure, I would just, and you just force yourself to do it. Write it in scientific notation. And then you do that a couple times and you'll remember. So there won't be any question. Because if you wrote 0.031 in scientific notation, it would be 3.1 times 10 to the negative 2. So that means there's only 2 sig figs. Likewise here. If you're not sure, write it in scientific notation. And then you'll get used to it. Then you won't have to keep writing in scientific notation after a while. See if you can get those. Oh, we're about out of time. So come by. I can make, if this isn't so crystal clear to you, try the homework. Come by and ask some questions. I can make this pretty easy for you. So just come by. So have a good day.